Yeah.
I finally did.
Yeah.
So I don't know what happened really. I am doing it all the time like that. So, but for some reason,
I think we are right on time, so I can help introduce you, and then maybe you will be the chair for the rest of the session.
Yeah, sure. Thanks.
Great. Yeah. So, okay, let's get started. So it's my great pleasure and honor to welcome Emil to give a talk about the discrete Morse theory, persistent homology, and Forman Ricci culture, which are very, very interesting topics for the conference. Yeah. Emil, please go ahead. Yeah.
Thank you. Thank you so much for the introduction, warm introduction, and thank you so much for inviting me to give this talk. I should say that while I talk about the subject, the title of the conference, of the slides, I made a change while preparing it. So I will talk more about the motivation behind all this work than I thought I would. So given this and the fact that it's I was still grading exams till yesterday, perhaps my talk will be less structured than it should have been. Yes, I apologize in advance. Now, I should also say, while there is only one speaker listed here, myself, this is work done together with many people whom I mention shortly. Okay, so so what it's all about. So the thing is that when you talk about networks and hypernetworks, first thing is to view them or consider them as decentralized polyhedral complexes. Why? Classically, and classically means still very recently, people would say, well, graphs and networks are the same, which is true and not true, because even a few years back, guys from social network would say, yes, networks, graphs, we don't know what graphs they are, they're not quite the same. So they were coping very hardly with the mathematical concept, but they are also a bit right, because networks tend to contain, to express something much more than just, the combinatorics, underlying combinatorics. Okay, so also I should say that when I talk about graphs, people are talking about, I don't differentiate between oriented and unoriented graphs. And of course, one would look at multigraphs and even pseudographs, which we don't really consider in geometry so much. But I won't make the difference. And in fact, most of the examples, or many of the examples I consider here, are oriented graphs. And I won't go into the technical details, because then it would be a mini course, not just a normal talk, and it would be boring, I guess. But a thing which should be mentioned, and which, for instance, both Arijit and Parvane mentioned earlier in their talks, is that classically in graphs, you look at node-based measures, classical clustering coefficient. And since this is basically nothing else but combinatorial curvature, then you think of scalar curvature if you want to do geometry. However, networks are not just the nodes, they are also mainly the relationship between the nodes, yes, between the speakers on feet or whatever. So then you consider, or have to consider, edge-based measure, which is rather new. And when you do geometry, for reasons which they mentioned also before, you're looking at tensorial quantity and vectorial quantity, and vectors are in graphs are just edges, then you lose like Ricci curvature. So that's why we will be talking about Ricci curvature recently. And then it's in late few years ago, people started looking at simplicial complexes and even more general polyhedral ones. Okay, so the first part of my talk is dedicated to this proposition of showing that there are a few good reasons to consider, let's say, simplicial complexes. So why? The first reason is it's a very simple thing and natural thing to do for a mathematician. So you talk about graphs and then you want to generalize them. So graphs are one complexes, so go higher dimension. Also simplices and polyhedral complexes are the backbone, so to say, of topology and even of geometry as applied in computer graphics, say. So it's very natural to look for them. Well, they're basic constructs. They appear in modeling different types of generalizations of networks, which are very popular these days. There are multiplex networks, which I'll exemplify shortly. There are multi-layer networks, and there are hypernetworks, whatever they might be. So I won't go there. I won't try to convince you, because everyone has a different idea what a hypernetwork is. So a hypernetwork, people say, so a graph is a network is a graph, therefore a hypernetwork should be a hypergraph. Well, but when you model them, that's not, people say one thing and model something else altogether. So that's a problem. But so we came up with a couple of ideas of how to do that. There is one way of transforming hypernetworks and multiplex networks into polyhedral complexes. This one is work with Melanie Weber, who's at Harvard now. She was at Princeton when he did that. And then there is a canonical way based on the work of Bloch, which is canonical, I mean, categorical in the sense that it's very general, any poset can be transformed into such a polyhedral complex. And then, of course, there is a trade-off, because what lived on edges, right, some vertices, but that's less important. It's a canonical way, and then it comes together as an Euler characteristic, and there is a close connection between Forman curvature and Euler characteristic. It's very nice and neat, and gives you Gauss-Bonne and so on and so forth. So the idea is that each time you have a path of length 2, like here we had a triangle. Each time you have a path of length 3, you add a tetrahedron and so on and so forth. Okay, so I want to dwell in this. So this is work which appeared recently with Arijit and his student Yadav, Yashar, sorry. And the third reason is, well, why should I look at them except that they're interesting as a mathematician? Well, they appear a lot. So there are a lot of things like that in nature, which are triangles and quadruples and tetrahedra and so on and so forth. So here is a small example from a paper with Melanie and Professor Yost. And you can see here these quadruples. This is a Zachary Karate Club. It's a real, small but real and classical social network. So you can have either edges and nodes, like classically. You can have filled-in triangles. But for instance, 4 points, you can have either quadruple, when vertices talk in pairs, edges, or when they all collaborate together to write a paper, let's say, then you model this as a tetrahedron. So it turns out that in nature, there are many, many such triangles and so on and so forth. And if you look here, these are a few classical examples, 2 social, 1 peer-to-peer email exchange, and a biological one. And you can see not only that, so that was kind of surprised at that time, and that's not that old, yes, a few years back. Not only that you have a lot of triangles, but you also have a lot of hexagons, for instance, in peer email exchanges. And I have to say that in the kind of biological networks, which I'll be exemplifying shortly, you have even cycles of lengths in order of thousands. So of course, it's hard to say how real or how manifest they are in the expression of those networks, but they are. So it's considering only simplices, as many people do, even this is even that an act of courage, let's say, it's kind of naive from the modeling viewpoint. It's very sane from the mathematical point of view, but that's all. Okay, so again, a simple example of pairwise interactions in PPI networks, protein-to-protein interactions. So two proteins which talk each to one to another or collaborate to produce another substance or whatever, you model as an edge. But if three proteins come together, then you have to model this as a triangle. Okay, so now why is it good for something? That's the first question. So the question is, yes, we try to look how it works on to explain or to better understand or to explore, if you want, the Waddington landscape, which is a classical model in epigenetic evolution. So you can see here, these are figures which are not mine. So we have a basic stem cell and it evolves and it differentiates, and as you can see, it differentiates more and even more, like here, so on and so forth. So you get this, I don't know, bone cells and hair cells and whatever. So Waddington thought of this as a ball who rolls down a hilly mountainside, waving landscape. So it rolls down, it gains more speed, loses some potential energy, and then get to this point, then it can differentiate. I mean, there are two possible paths and so on and so forth. So this is a very nice model. So people in biology like it for tens of years. But is it good really, or is it just a metaphor? So recently, people try to discretize it, and when you discretize it, it's clear the idea is to pass to networks. So this is work of Wong. It's based on the quantization and of cellular trajectories and pluripotency. And what you can see here is a small model of such a network, part of what I'll exemplify. Okay, so since you are talking about edges so far, and since these edges are not just combinatorial, they come up with weights, yes? So it's quantization of cellular and pluripotency, so you have weights attached both to nodes and to edges. Because when you do chemistry and biology, there are strengths and relevant weights of this attached to these connections. It's very natural, and for computational reasons as well, because these even smallish ones are in sizes of hundreds of thousands of nodes and edges, and they are not tree-like. It's very natural to have Forman curvature. There is one more reason to look at Forman curvature, which I'll explain shortly. So this is a formula. I just said that, well, Emil will explain, or Parvane, but if I would go back and explain why this is the formula, then we'll have another talk altogether. So suffice to say that if you want to look at the curvature of an edge E, all you take in account are the weights of its endpoints, W of V1 and W of V2, and the weights, its weight, and the weights of its incoming edges, like here, for instance. Okay, so this is a very simple formula, and really for smallish networks, like very sparse one, like they appear in chemistry, a lot of times you can do it by hand. Of course, it will take time. It's better to use a computer, but you could. Yes, it's elementary. Okay, so in combinatorial case, this is just 4 number minus the number of the degrees of V1 and V2. And then you can apply this, and what you see, first results, you can see here. This is for stem cell differentiation. So of course, you can, the basic idea, which is of Sandu and Tannenbaum, is to look at entropy. And so entropy, it's clear why, because you have, there is a more disorder when you have a stem cell, because there are many more possibilities how it evolves, how the way it evolves and settles down to a finite state, the entropy is got down, yes? So the first thing is to check them, and you see it's a very, very nice, almost one correlation between these two. If you look at melanoma, we get the same results, but of course in melanoma, you start with a cell which is normal, it's ordered, and then it's chaotic, something worse, bad goes there, and that means that entropy increases. And indeed, curvature increases as well, yes? So we saw that there is a strong correlation, and since this is much more, entropy is kind of philosophical notion, at least, when you talk about graphs and stuff like that. Whereas Forman curvature is a very precise, simply defined notion, more easily to interpret, and therefore it's good to have it at hand to use it to understand this kind of networks. And this is the first time anyone did it. Now, what you see here is a formula for Ricci curvature when you plumb in faces. Well, it doesn't matter if you plumb only triangles or tetrahedra and so on and so forth, because Ricci curvature lives on the intersection on edges, this i.e. on the intersection of faces, therefore only the two skeleton matters. So this is a formula. So then you look only at the weights of the edge, the nodes, its end nodes, and the adjacent faces. So I do something not very nice. I go back to one of these pictures here. Sorry, my apologies. So here, for instance, which edges appear. So you take only, you either look at the weights of these two pink faces because they have in common but no other edge in common, or you look at those edges who have the vertex in common but not the face as well. Okay, so stuff like these are called parallel. It doesn't really matter here. You have a formula just trying to make some sense out of it. It's slightly more complicated than the other one, but it pays to work with a more complicated one. Mathematical viewpoint, it pays out because it's closer to the original concept. So the one-dimensional Forman curvature, the graph Forman curvature is just a reduction, a limiting case. So of course it loses some of the flexibility. This is a classical one, so to say. Insofar as classic combinatorial notion can be considered classical when you talk about Riemann and geometry. And so it's more expressive, yes, it's better. So indeed, you can see here, it's correlated, the two full Forman curvature is also correlated with entropy and 1D, but correlation is stronger, even if it's anti-correlated, because you can have, the signs are kind of different because addition of the faces. So this was done for stem cell differentiation. We did the same experiments basically with cancer. And then, of course, the evolution is the other way around. Again, in stem cell evolution, entropy goes down in time, whereas in cancer evolution or disease, it goes up in time. Yes, it increases. Okay, so these are the legends. And I won't try to go over all these details. Otherwise, this is not a talk in biology, and I am not a biologist myself. Yes, I'm still a mathematician. Yeah, even if though in more applied directions lately. But they say that a picture is worth 1,000 words. So a Venn diagram, which is a simple picture, should be at least 2,000 words. So we compare the curvature detection of statistically significant genes to the classical differential expression method, which is bread and butter in gene biology. And it turns out that, as you can see, Forman curvature, be it 1D or full 2D, it's much more potent at capturing this or detecting these problematic or important genes than biological notion of differential expression. And as you can see, it's so the both curvature, when I remove the intersection, both curvatures together are 20 times more effective almost than differential expression. And as you can see, Forman curvature, the full Forman curvature is even more expressive. So that's indeed proof of capability. So it shows not only what Forman curvature can do, which is very nice for us, but of course, for a mathematician, it's important to say, well, I was right. I mean, mathematics is good for something, and it can capture stuff which biology itself, which may explain it, but it doesn't really find them very easy. Okay, so in conclusion, you can use either of those, but the two-dimensional model is more expressive. As geometry implies, results also show that the 1D is just a skeleton, so to say, of the full interactome. And of course, it would be nice to consider higher order all cycles and higher dimensional ones, and so on and so forth. And so what it shows is that curvature increases in pro-cancer pathways and decreases in tumor suppressive pathways. Therefore, you can look at curvature as an indicator of functionality in cancer cells, for instance. Then, and this is a hope, we might use it as a potential tool in therapeutic strategies in cancer, because there are groups of people in Minneapolis, for instance, which are trying to reverse this entropy thing, I mean, to transform this mathematical tool into therapeutic methods. I mean, to really try and to cure cancer and to reverse evolution, so to say. And there's a hope that our tool might help them. Okay, so that was a second motivation, taken a step further. I mean, you have a lot of such faces, two faces and higher dimensional ones, and using them is very helpful because it enhances your toolbox and you can detect much more things with practical implications, like in this case. And this is work, I should say, before going further on, is work we've done with Kevin Murgas and Romer Sandu from Stony Brook University. So biology is all there, yes, of course. Now, the third motivation, I said I'm going back, so I'm trying to explain why you should not look at graphs, but at polyhedral complexes. So the third motivation would be the fourth. It would be that people are canonically doing what is considered a clique simplex. They are adding these triangles and why? Because they want to do persistent homology. So, which is in topological data analysis, is all the hype recently. Yes? And it's more and more popular. And there are a few very nice papers about that, theoretical as well applicational, so people know about it. So one way of doing it, and which we suggested, is to use Morse theory, more precisely Forman Morse theory. And the way to do it is precisely using this clique simplex, but not just in adding more and more things, but doing it in a gradual manner, in an educated manner, so to say, which gives you some control and better understanding, and it's not brute force. Yes. So of course, these are the people, these are the faces behind the names. And so Forman should be here anyhow, because I mentioned his name before. And there is a classical, so Forman's work, Forman was a student of Bloch. I think he was his last student. He did work not only on his curvature, which is not as well known, plus published work, and it's more technical, not that well presented, so to say, sorry. But he is very well known for his discrete Morse theory. And that's applied a lot. I mean, in graphics and imaging for 20 years, I guess, and beautiful results. So what's the idea? It's not, it's a discrete notion of Morse theory. It works on simplicial complexes. So from the beginning, you have to build them. So you have, when you talk about Morse theory, you need Morse functions. And these height functions are not continuous ones, as in classical theory, but discrete ones is just, you just put a number to each simplex, to each phase. So the idea is to put the number to assign a higher number to higher dimensional phases. The higher the dimension, the higher the number. And you are allowed one exception, no more. So here you have one exception, if you will see. But here you have two such exceptions. You have 0, 2 is greater than 1, and 4 is greater than 3. Therefore, this is not a discrete Morse function, and this one is. Okay. So this is indeed a beautiful theory, and it's beautiful not just because it's neat, but it's also efficient. It captures the classical theory and its connection within topology, I mean, both homotopy and homology, and it allows you to construct proper Morse functions using what it's a Forman called a discrete gradient vector fields. And these discrete vector fields are precisely what people love so much in imaging. So not that much the homology stuff, but more the discrete gradient vector fields. Okay, so how can you use that? So we had the idea of applying that. So this is a paper again with Arijit and a student of his and a colleague of his on persistent homology. And you build a click complex, and this gives you a filtration scheme, which is shorter, reduced, therefore is more efficient in computation. It's very important in this when you have big networks. So to do that, so again, Forman's work is combinatorial by nature. So you just it's a counting stuff. But so if you want to make it work nicely, you have to so these simplicial examples. But if you want to do height functions, you need to have weights, which are not one all the time. Therefore, you have to transform a weighted graph or weighted network into a weighted simplicial complex. So I should say the accent I should place it is from passing from unweighted to weighted, yes, because we are already familiar with the ideas passing to higher dimensional objects, and this produces, of course, a finer filtration. And technically is done by introducing some level subcomplexes with critical weights. So this is the first time somebody used these ideas together in complex networks. And I don't know why I can't seem to be able to. Sorry. I don't know what's, okay. So here is an example of how it works. So that's how you construct the filtration. And you can see the barcodes of the 0 homology and the 1 homology as they appear. And you have, so you pass between critical weight 2.35 to 3.48, and you have these intermediary stages, the sub-complex which I was talking about. Okay. Okay, so that's what we did together. And then, now again, I have the same problem. Okay. Now, of course, when you have weights and simplicial complexes, then at least when you talk about graphs and stuff, then it's very natural to think about Forman curvature and to use Forman curvature as a height function. So that's something which I did and in Java did separately, and they tried it. So you can see again the filtration in the example. And what happened is to them the puzzling thing at point in time that if you look at the results, these are the results obtained with discrete Morse, Forman Morse theory, and this is done with the Forman curvature filtration. The results are embarrassing the same, almost the same. Yes, this is distances between networks are computed using the bottleneck distance of the barcode. Yes, There are technical ways of doing it. So they were a bit afraid that, except the name Forman, there is no common ground between the two. So there was kind of, they were puzzled why the things are the same. So that interested me, and now I'm going finally to that part of the talk, which is related to the title. This was the motivation, yes? We have two methods. One is Forman Morse theory, the other one is Forman curvature, very different, both devised by Forman for different needs, and they give basically the same result. Why? So the answer is, I don't know what's happening, sorry. Okay, so the answer is that if you want to understand why this is happening, it's better to go back in time and to think that, to remember or to recall that the first discretization of Morse theory is not due to Forman, which is much more popular these days, but it's also more esoteric. It's more popular because it's combinatorial, and people in computer science learn a lot of combinatorics and graph theory, but they learn very little differential geometry or geometry in general. But there is a notion which was devised much earlier by Thomas Banchoff, and which is much more intuitive and easier to understand. So his discrete notion is for PL spaces, if you want triangular meshes or whatever, yes. So they have to live in some Rn. Okay, sorry, it's taking me back for some reason. Okay, so to understand it better, I'm doing it on GIF because I think there is not much more time left, is that, I mean, there still is, but I still have things to present. So if you want to understand Banchoff's ideas, you have to go back to Morse work. So you go to the index, so you have a point, a surface, and a direction, and you define the index. Yes, you can see here for these points, typical points, the catastrophe points, then you'll have the indices, which are 1 or -1, depending if you have a minimum, maximum, or saddle point. Okay. But in a discretization that won't be easy to implement, the thing is that if you have, you should look at things differently. If you have a minimum or a maximum, a small circle around this point won't intersect the surface. Whereas if you take here a small circle, it will intersect this in 4 points. Okay. And this is a critical point. And if it's an ordinary point, there are just 2 points. Okay. So my apologies. I have to remember not to do the natural thing. So how do you do it in polyhedral surfaces? In short, you do the same thing. You have a different, still have a height function of general direction. And you have only to understand what's happening, what are small circles. So of course, small circles in polyhedral surfaces, let's say it's just the star of the vertex. Yes, so polyhedral disks, more precisely. And so, as you can see, it's easy to differentiate between the two cases when you have a ordinary point or a extreme critical point. And you can see here, this is a polyhedral surface, and you can see that the index here at the maximum points you have it's 1, whereas here you have a degenerate. How you can do it not by looking at it, you don't have to look at it, especially if it's embedded in some higher dimension, whatever. It's you look at triangles. So you look at how many if you have a vertex and if it sits in, it separates the tangent plane here separates this vertex, the other 2 vertices of this triangle, then this is called a middle vertex. And I'm sorry, so it's easy to see that the right way of discretizing the notion of index. So Banchoff's approach is to look at the index of a point with respect to a direction. It's to just to count the number of triangles who are the middle vertices for this direction. So this is a very simple formula. It's a combinatorial. You just count them, go one big loop, and you look at all of them, and then you take their sum, and beautiful surprise, their sum is precisely the Euler characteristic as expected from the classical system. Okay. So putting things together, first conclusion is that if you look at hypernetworks, multiplex networks, or just networks per se, as interpreting connections as faces. And by the way, they don't need, as you saw in previous examples, they don't need to be just, you see, they don't need to be just, sorry, I don't have it nice. You don't need them to be just simplices. They can be quadruples or whatever, pyramids, and so on and so forth. So given such a hyperstructure or generalized notion of network, you view it as a polyhedral complex. Therefore, you can look at it from the perspective of Banchoff's discrete curvature, discrete Morse theory. It satisfies all the properties. You have height function, critical points, and so on and so forth. Therefore, you can do persistent homology because you have a Morse theory. Thus, our first result is that there is a discrete curvature-based persistent homology scheme for networks, because I should say Banchoff uses his index to define Gaussian curvature. Okay, once you have Euler characteristic, it's very easy, or very similar as developing the index. And then one can ask himself, well, you have two notions. This is new, is simple, I understand, but it's kind of new to me. People are using Morse here, Forman's work. Is there a connection between the two of them? And the answer is yes. And the answer is due to a guy named Bloch, and who said that for any finite regular CW complex, very general, basically, and any discrete Morse function for it, you can embed your object in some higher dimension, need an embedding. So, and then the cells that are Forman critical, remember in Forman's Morse theory, cells are critical, whereas in Banchoff's theory, vertex are critical. So once you do this embedding, critical cells become Banchoff critical cells with respect to their barycenter. So to each cell has a barycenter, and that one is the critical one. So basically they are the same. Yes, we can pass from one to another. Of course, but of course you do this duality stuff. You look, instead of a cell, you look at its vertex. Okay, so that's what Bloch observed. And then we can ask a bit more. I try to be on time, don't worry. So there are some stronger results and even more surprising. One is that Forman more discrete Morse theory is in fact more accurate than smooth Morse embodying homology. And even more, if you want, even more, in dimension smaller than 7, classical Morse theory and discrete Morse theory are equivalent. So in fact, these discrete notions of curvature of Morse theory are as potent or even more potent than the classical one, because we know the results of Morse theory. We can transform Morse into Banchoff, which is very natural, and then we can do the same. Okay. I don't know what happened with navigation, but thus the conclusion is that there is a Forman discrete Morse theory based persistent homology for hypernetworks that produces a minimal or almost a minimal number of critical simplices. Okay, that's a concatenation of the things. forth. So what can we say about these two theories? Let's compare them briefly. So Banchoff is much more intuitive. I can draw it, yes, I don't have to imagine. And I really see height functions. These are objects in R3, no problem. The minus is that, of course, in higher dimension, everything is very formal, at least harder to see, yes. On the other hand, if we should just have data, then Forman is much of this easier to implement. The minus is that Forman Morse works for unweighted hypernetworks, and you have giga of them to use weighted ones, whereas if you use metricize, transform them weights into a metric, then this metric is, you have a polyhedral metric, and then can apply Banchoff general. So you have proper notions of curvature in the combinatorial sense of them. So there is a restriction on the type of spaces on which this hold, which is not a problem for us because this is exactly the context in which you are wanting to work. But even more so, even for more general structures, much more general than just simple convex cell complexes, you can apply what another result of Bloch, the so-called stratified Morse theory, which takes into account this kind of things, which is indeed the most general we can deal with it. Okay. So then the problem is that Banchoff is very intuitive, very easy to use, but it's hard to use it in higher dimensions. So you would need to embed it, and that's kind of difficult. And the trick is, and with this I come to the end, the full circle, you can use Forman Ricci curvature. Why? Because if you look at the combinatorial version of the Forman Ricci two-dimensional one, the Ricci-Forman curvature of an edge is just 4 minus 3 times the number of the triangles adjacent to it. I'm just talking here about the simplicial complexes for simplicity, minus the degrees of the endpoints. So just counting the triangles which come in fact, this is what, and this count is basically the index, yes, gives you the Forman curvature. And this, on the other hand, or moreover, you can transform, look at the scalar Forman curvature, which is a mean of average of this, the Forman curvature of the edges, and then the scalar curvature of a vertex V, it's nothing but 2 minus 2 times the degree of V minus the mean degree. So in other words, the scalar Forman curvature, so which is Forman curvature of vertex, is nothing but 3 times the number of the combinatorial curvature, the classical one, which is easy to understand, well, as is used in graphics, minus 4 minus the mean degree. Thus, you can apply, look at this one, which is very expressive, which appears basically in Banchoff theory, but computed through scalar Forman curvature is very easy to compute, and yes, you just pass from this geometric concept to a very simple combinatorial one. Oh, I keep doing this mistake. Now I'm kind of trying to finish it on time, and therefore I keep forgetting even more than usual. So the conclusion is that not only exists a persistent homology scheme for hypernetworks based on Forman Morse theory or on Banchoff Morse theory, but it's a very simple persistent homology scheme based on Forman Ricci curvature. And as you can see from here, this is basically the Banchoff, or if you want, and which is equivalent basically to Forman's Morse theory, and this is based on Forman. This is Forman curvature, so it's basically the same. That's what explains the surprising result observed by Origin that Forman Morse theory and Ricci curvature obtain basically the same result because they are basically the same. So this is the essential theorem. And all these results, and of course, pertaining to the second half of the talk, to the more technical, the Morse theory and the connection with Morse Forman curvature can be found in this paper. Okay, so I think I'm finished on time. Thank you very much. And questions?
Yeah. Any questions? You can just unmute and ask. Yeah, you have one. Hey, Junjie.
Yeah, hi. First of all, I want to say that I'm very happy to see that the Forman Ricci curvature could have such a good classification performance in the stem cell differentiation and the cancer data, because we work on this Forman curvature in this biomolecular data, and also similarly achieve similar type of this kind of the pictures that you have shown in your first part of your talk. Yeah. So the second thing that I would like to ask is that because this Forman Ricci curvature is a more combinatorial one, and it's also good, and it's also very very pleased to see that you can actually show that there is a Forman Ricci curvature based persistent homology scheme, because we propose this actually we propose a sort of persistent module on this Forman Ricci curvature. Yes, nice. In the biological applications. But is it possible to further extend this theorem further? Because this Forman Ricci curvature is also connected to this Hodge Laplacian through the Wagner-Weizenburg decomposition. Yes, so is it possible to also conclude that there's a persistent spectral based persistent homology scheme?
Yeah, well, I think you are right. That should be true. But I can't be sure. I didn't work on that yet. I mean, okay. But it's a good idea. It's very natural to look at that.
Then is it also? Sorry. Yeah. Please go.
I'm just sorry to say that, of course, Bochner, look at the Bochner Laplacian and the spectrum, it's very natural. But somehow we never got to that. I mean, it's easier to obtain results through this, but of course it's something what we should do. I think you're right.
Then another possible kind of thought that I want to not sure whether to say to suggest or this, but another version of this discrete Ricci curvature is the Oliver Ricci curvature, which is a completely differently formulated compared to this.
Okay, no, it doesn't really work here for a number of reasons. It's very popular. It's an amazing mathematical thing, and it works very nicely in communication networks. Here, it's not the proper tool. I mean, I won't go into the biology why you don't have the broadened motion. But moreover, on the other hand, it's very hard to compute it. I mean, these are very, very large networks, very dense. And it's prohibitive. I mean, you do it for images and it's you need muscle to do that, even for small images. And more importantly, it's not good. There is some work of Asuden, Evans, and Melanie and myself proposed a method, but it's not very natural, or not very easy in any case, to extend Olivier to higher dimensional ones. Remember, it was invented for Markov chains.
Yeah.
So
yes.
If you want to look, you have to look at higher order, higher dimensional complexes. It's not what you want to do. Olivier is not meant for that. I'm not saying you can't do it at all. Yes, of course. Mathematically, you should try anything, and computationally, in any case, it's not the natural thing. So that's one good thing about, I mean, in computation, we know that Olivier and Forman are well correlated.
Yes.
But that's good in any case to have more than one notion of curvature, because each one captures different phenomena and can be applied to different problems. So nobody should be insulted that his curvature doesn't work on this problem. It works on other problems better. Yes, it's a democracy of curvatures, I would say.
Yeah. Yeah. Okay.
So, I mean, you don't have to be partisan about this. You have to decide which one is best to model a certain problem. That's all. And of course, I like PL topology and geometry. That's why I'm using Forman more. Okay.
Yes, because the Forman Ricci curvature is the computation is lighter.
Yeah, it's much more geometrical. Yes, in that sense, it's polyhedral.
Yes. Yeah.
Okay.
Thank you.